like I just made like a Manitowoc Minute style exclamation or something. Let's put that there. Okay. Move. See, this always happens. Okay, come on. I know this. I need just to make a freaking to-do list. There we go. 66. I hope I selected the right audio source. Yeah, sure. Okay. All right. Ten seconds to go. Good morning. Hope you're doing all right. Monday, April the 20th. It is 11 a.m. All right. Move this thingy over to the other side. Do a round of announcements first here. Just to say, did you start homework 10 yet? Please think of, if you have not done so, please start. Quiz 9. Quizzes open on Tuesdays, and just to give people time, they are due Wednesday, so we'll have it due at the end of the day Wednesday. Response is due at the end of Wednesday as well. Let's do a little like kind of office hour like moment first. So I'd like to just review, and hopefully admittedly a little older of a problem, but I think it will be good to do. So let's take a look. Oh, come on, where's my mouse? There we go. I would like to, as a group, talk about if j from x to y is surjective and k from y to z is surjective, then k compose j is surjective. So in order to prove this, so the general principle, of course, is that every time you see anything inside a thing you need to prove and there's a definition that's relevant, you probably need to bring that up. If that definition doesn't come up, probably something's going to go wrong. So for example, I have at the near the bottom of the screen a recall of it's not in the original language of it, but it's essentially all there. So if you have a function r from h to I and a function s from g to h, then the composition is r compose s, right over there, from g to I, with rule r compose s applied to g is r of s of g. Now, I think I should admit the same thing that is probably on your mind, which is, how do I remember this? I don't. I don't actually have it memorized. What I remember is the rule part. That seems very reasonable, I hope, that r compose s of g equals r of s of g is the more memorable part. That I appeal to how you had to deal with composition in Calc 1, Calc 2, this kind of thing of like, oh yeah, you follow the letters in that order, right? If you scan from left to right, you see that R, then S, then G. Then same thing here, you see in order R, then S, then G. And then what you do, how do you recall this business about which is the domain and codomain, is you think about what's going on right over here and go, let's see. So you're going to do r of s of something. You don't even know that it's a little g yet necessarily. Little g is, of course, suggestive of the capital G, but what I mean is like you have r of s of a thing, of something. What are you going to feed into s? The only kind of thing you can feed into s is something from g. So that's why I chose to use a little g over here. But then you feed that in, and then S of G ends up being something in H. And since you have something in H, that's the kind of valid thing to input into the function R, and you get as an output something in I. So that's what helps build the codomain, the domain and codomain being capital G and capital I. I hope that makes sense. Are we just on board with like it's meant to review the definition of composition, but also just kind of let you into like how I'm thinking about how do I recover this information without having to go look it up. I hope that's like gives you a natural way to look at that. Then we should apply this, right? So let's take a look here. We've got a function k compose j given in the problem. Well, so then the j, I wrote it directly above the r compose s. Take a look, plug in a j everywhere you see an s. Right, so I wrote the j right above the s. Since we were told up here that j is from x to y, you'll notice right here you've got to plug in, just by writing it directly above, I hope you're seeing what I'm trying to do is indicate that we got to plug in a capital X every time we see a capital G and plug in a capital Y every time we see a capital H. So I can already go ahead and plug in the Y where the capital H is. And if this works out, then K, the other function, oh yeah, domain there, codomain of Z that's up here should go in this spot. So what shall we say is the domain of K compose J, and what shall we say is the codomain? Make sure we're all okay and together on this. We'll wait till it's awkward. Okay, x to z, right? Of course, with rule k compose j of x, if you want to use a little x here, is k of j of x, right? So that's us applying the definition of composition. Why is this relevant here? So now, of course, we have this j from x to y surjective that was given. Of course, we have a second given in this if part, so we've got this second fact, k from y to z is surjective, and now it becomes much easier, having said what we have down here, to take this and say what we want to prove, of course, is that this is surjective. Right? That's so now we have a mention of the domain and codomain here. And this other piece about the rule, let's just kind of keep that off to the side for reference for a moment. The other thing we'll need, so there's these two boxes at the top. These are things that we need to use. We have this box at the bottom, something we need to prove. The other thing then in this, so having dealt through the if, proving the if-then part of this, now we need the definition of surjective. This is something that I don't want you to just always be looking up. I want you to think about this in a very natural form of everything in the codomain is an actual output. So for each thing, maybe we'll call it C in the codomain, there exists something in the domain such that this function here is named f. So f of domain thingy little d is equal to codomain thingy. Right? So based on this definition, we should write in what it translates into for j to be surjective. So we get here for all, I'll use little x if I can get away with that here, for all, nope, wrong, I need the codomain thingy, for all little y in capital Y, there exists a thingy little x in domain capital X such that j of x is equal to y. So all this is just like over here, this translates into that. Every capital D is now a capital X. Every capital C is a capital Y. Every little f is a little j. That's all that happened, right? So this definition allows you to translate back and forth. Same deal over here for what it means for k to be surjective. I'm actually, just to illustrate the point, I mean, whenever you have a variable as part of your, you have a variable that's being used in your quantified statement, that's always a placeholder variable. So just to make a point, I'm going to use new variables here. I don't know, how about for all m in the codomain, there exists n in the domain such that k of Domain, which one's the domain thingy? Oh, it's y. Yeah, so k of domain thingy equals codomain thing. Okay, so that's again a use of this definition, an understanding of this translates back and forth, right? So we've done actually two translations this way. We actually have one more, which is down here, right? So same deal. Now the thing to do is to these blue boxes. Same deal again. It's if you have the function. And now the function name isn't little f, but it's k compose j. Same deal here. So I could put a k compose j here and a k compose j here. Okay, you should do this. This definition of surjective applies to any function, and I know it was called f in just the definition, but it applies to k compose j as well. So we would have here that we haven't used, I guess, c's and d's. So let's go ahead and do that for all thing in codomain. Oh, that's why we wrote down what the codomain here was. It was this z. So for all little c and capital Z, there exists. Let's just go with little. Let's go. Yeah, let's just use this little d here. There exists d in capital D, such that k compose j applied to d is equal to c, right? So this is us now taking the idea that this translates into that, right? If we were to have what's in this box, you'd get that. That's the very end of the proof. So I'm now going to get rid of this down here. So sorry, this is not running like lecture right now. I'm trying to do this a little more like what would happen in office hours for a topic like this, and say, so look, as soon as we know this is true, then we know this is the final thing is true. So we could even sort of like get that last thing mostly out of view at this point. So think about it. We from this, we use this to prove that. Now that we know this is true, we need to use this and we need to use that. But if you want to use a statement that starts for all, goes back to the principles that we looked in the fourth week of the semester, you need a thing in y in order to use this box. We don't have that. To use this box, you need a thing in z. We don't have that. Over here, this is not a box we're trying to use. We need to prove this, right? So to prove that, let's start writing a proof of this kind of right about here. Well, to prove a thing that starts for all, this is why, like, even in just the recent-ish homeworks graded, you're seeing this thing of like, the thing you need to start starts with a for all, and you don't include that information, you're not going to get credit for it, right? Because sometimes you'll get through a proof because somewhere else later on in the statement you have kind of what you need almost for free, but like this goes back to using and proving a for all. And so because the thing we need to prove starts with this for all, we got to do a let C and Z. But what do we do with this now? This is for everyone. I mean, yeah, what we need to prove next is, well, I'll underline it in green, but what do we do with the fact that we have written let C, B, and Z, which is for everyone? Question for the whole group. I'll just move things around. Okay, yeah, so we eventually need to define, because of what's underlined in green needing to be proved, we do need to define an appropriate thing that belongs to capital D, agreed, and then prove the condition. But how are we going to do it, right? We need something in capital D. I can't think of something in capital D at the moment. But so I guess my question, to try to make the question more pointed, is what do we do with this now that we have a little c belonging to capital Z? What good does that do for us now? Can we do anything with that? So the comment being made about defining an appropriate D in capital D, totally true. And that's our final goal. But like, what should we do then to get there? And how does having this little c in capital Z help? Use the fact that k is surjective, right? Yeah, okay. So yeah, being said two different ways, thanks. So since we want to use this for all statement, we now, right after that comma, We write all the text after that comma, plugging in for every m, we plug in a c though, right? So we now know there exists n in y such that k of n is equal to the m is what gets replaced with c. So this is, I mean, this is the, like, what I'm trying to get at here is this is the general principle that happens kind of over and over and over. It's been happening week after week after week since the fourth week of the semester to talk about, like, how do we use and prove these things that have these quantifiers. Now you could split these into two separate if you want. I don't really much have the room, so I'm not going to do that. But we have these two facts. We've got a little n that belongs to y, and then we have this fact k of n is equal to c. But now that we have something in y, we can, same deal here, right? We have there exists little x in capital X such that j of x is equal to n. And I notice my own little error in what I had down here. Like, I wrote a d here, just copying the d that was in how we cited the definition. But remember that if I just scroll down for a moment, you'll see it here that that domain in the specific function was a capital X. Oops. Okay, so that, okay, things like that happen sometimes. So look, we need to eventually define a little d in capital X instead. So sorry to have it thrown off. I appreciate the earlier comment was right based on what was there earlier, but we need to define a little d that belongs to capital X. Well, it's now helpful that we have little x in capital X. If now it's up to you, it's a matter of a little bit of personal choice of whether you're going to write let little d equal little x or whether you're just going to use little x to be the little d or whatever, right? So just a little bit. I'm just, this might be a little longer to write it this way, but just to not to underdo it, let's say, just to make the point. Like, the point here is, so then we can claim, right, that d belongs to x, and then finally we still need to prove the condition as was mentioned. So we've got this k compose j of d, and what's that going to be? That's why I left this over here. So what the rule does is this allows, take a look, we're taking this thingy as if it's a formula and plugging in every little x with a little d and having k of j of d, and now I can get rid of that. And then the point is this becomes k of j of x, because you can, every little d is little x, that's how we defined this. And then I'll write the k of part. This in the middle was j of x, and that we have over here is n, and then k of n from what we have right over there becomes c. So this is our proof that k compose j of d does end up equaling c. So I know this is maybe a little long and drawn out, but this is, I'm trying to model this idea. It came up in some of the comments that I would like to see, more proofs of injective surjective, and certainly we've been doing that last week with cardinality, and you'll continue to see this. But the point is, I hope what you're seeing is every definition that gets brought up inside a problem, you probably want to look that up and apply it, and always think about using versus proving. Think about if you have like little x belonging to a set, I don't know, capital S, and S is defined a certain way, apply those principles. Like the process we're looking at, it always keeps doing this kind of game. It's the only thing that happens actually in our 400 level proof based math classes, and that's what Math 225 is about, right? It's about getting, for math minors, maybe you're like, well, why am I doing all this? But like, that's the class you signed up for, and that's what I said on day one about what this class is. It's a boot camp, if you will, for getting people ready to prove things. Like, this class is how to do the proofs, and then the next classes like 411, 407, 415 are like, cool, let's now go in a specific area of math and apply these ideas to do the proofs. So let's just recall some quick ideas, and then we're going to see some rather bizarre proofs today. Two sets A and B are equicardinal if there exists a bijection from A to B. So the overall point, or the note or moral, right, is to prove that A and B are equicardinal or have the same cardinality, you need to, step one, define a function from A to B. It'll turn out, if you instead want to define a function from B to A, that's going to work. But by define a function, it's the usual thing of you need to provide a domain, a codomain, and a rule. So the domain and codomain are almost given to you because you're usually given these two sets and you got to then deal with them. Like, so one of those is domain, one of those is codomain. It's the rule that's hard to come up with. And the rule needs to be good because once you define the rule properly, then you need to prove that this function is bijective, meaning prove that the function is injective and surjective, right? So the rule part is challenging. I have to admit that. The rule is challenging to come up with. So this is the part where I would suggest you do things like draw pictures to kind of represent what's going on. Draw like Venn diagrams. Think about people waiting in line for sandwiches. You saw sort of pictures that, even though it was drawn more sideways last time, ideas like, zigzagging like this. All of these are very informal as ideas, but it helps to have a kind of informal cartoon way to look at what's going on first, and then take those ideas and then make them precise. Like turn them into some kind of piecewise function that alternates if that's what's going on, right? We had last time seen this definition that a set. Oh, geez. I think this pen is running out of batteries. A set S is countable if it is finite or equicardinal to the set of positive integers, and a set that is not countable is called uncountable. And you can kind of work through some of the language of what's a countable set that's not finite. The only option is this other thing over here of equicardinal to positive integers. So this goes by its own fancy name, right? That countable infinite set is called countably infinite. And the basic, so even though that's the official definition, what you could essentially almost morally say this translates into, so essentially, so there's the definition, let's say, but then essentially, then a set S is countably infinite. So definition's up there, but let's just, for the sake of like processing several definitions at once, say this happens if and only if there exists a bijection, say from set of positive integers to S. Of course, you could switch which one's the domain and codomain, but I tend to really prefer, and I would strongly suggest you, whenever possible, if one of the two sets is going to be set of positive integers, I think it's much easier to just make that the domain, because you always do things like f of, and then it's nice to know what kind of creature you're talking about. S might be a set of people, or dogs, or whatever. So I think it's just generally more helpful to put the domain there. Okay. I need to maybe bring up this. So this language is maybe not ideal, but why the word countable? So why is this word being used? The idea here is that you can count. If you have a countable set, even a countably infinite set, they're saying that you can count. You can count on your fingers. If you have an infinite number of fingers. So it's a little strange in terms of idea of like 1, 2, 3, 4, 5, and then you run out once you're at 10, and then you like borrow somebody, you get your friend, they're like, hey, can I buy your fingers? And you're like, okay, that's 11, 12. That's sort of the idea behind this. Or if you want, you could think of this as there's something sequential going on, right? So there's this sort of strange optional questions I asked about, like, one bus shows up to an infinite hotel, and does everybody have a room? And this idea that once reconfigured, everybody still has a room is this idea of that there's a sequence, right? So if each person still has a hotel room based on a certain number, and this sequencing idea I'd like to use, so it's sort of an informal version of existence of a bijection from set of positive integers to S. It's this idea that there's like a first element of S and a second element of S. Of course, sets don't have order. There's not technically an order, but let's informally talk about the first element of S and the second element of S. But we're not going to talk about like the 2.7th element of S. No, so it's sticking to whole numbers, first element of S, second element of S, third element of S, and so on. So I'd like to prove to you, at least based on this very informal way of thinking about what countably infinite looks like, this theorem that the set so this is not all rational numbers. This is just the positive rationals with that greater than 0 written. And rational meaning integer divided by integer. Okay, so this set is countably infinite. Now, our normal approach would have been to provide a bijective function and state its rule, but we're gonna go with this sequential idea that, let me tell you what I'm gonna say is the first element of this set, and then what's the second element of the set, and what's the third element of the set. And this idea then is like, that's gonna be my bijection. So I'm not writing it out in a formula form. If you'd like to afterwards, I challenge you to give it a try. But I would like to first of all write the following kind of rather big picture. So I'm going to have here 1 over 1. And then on the next line down, I'm going to write 1 over 2, and 1 over 3, and 1 over 4, and 1 over 5. And this goes on, so I'll draw some dots, saying I don't have time to keep writing that. And then if I move over one column, I'm going to have 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, and so on. And then the next column over, the numerators will not be 2's anymore, but the numerators will be 3's. So 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5. The next column over, numerators are 4's, 4 over 1, 4 over 2, 4 over 3, 4 over 4, 4 over 5. And one more column. How about 5 over 1, 5 over 2, 5 over 3, 5 over 4, 5 over 5, and so on down that way. Of course, these rows go on forever as well, so I'll draw in some dots to kind of indicate that. So what I want you to notice is that if you go to the right, you always increase the numerator by 1. And if you take a certain fraction you're looking at and you move down in this picture, then the denominator goes up by 1. So said differently, starting with 1 over 1 in the upper left corner, in this first row, all denominators are 1. In the next row, all denominators are 2. In the third row, all denominators are 3. So where are you going to find the fraction 21 over 6? You've got to go over to the 21st column and then go to the 6th row. So I would like to tell you a sequence in which to put all of the numbers so that we have sequenced, sequentially, like what's going to be the first number in this set, the second number, because we've written out over here all of the positive rational numbers. And if you just go down the first row, you won't ever get to the second. Sorry, if you go just down the first column, you'll never get to the second column. If you go just reading across the first row, you'll never get to the second row. You'll never get there because the first row with these dots goes on forever. So you have to do something more creative, and there's lots of ways to do it, but what I'm going to do is say, let's go there. Let's look at 1 over 1. So that rational number, of course it's simple, 1 over 1 simplifies to 1, but I'll just keep it written as a 1 over 1. That's going to be my first number. So that's f of 1. And then what I'm going to do is move along this diagonal. So there's this one and then that one. So then 1/2 and 2 over 1. So this is f of 2. So I'm telling you my function, I'm trying to get you to this idea of this function f from set of positive integers to this set. And what I'm saying is that first circled thing is my f of 1. So f of 2 is 1/2 and f of 3 is 2, or 2 over 1. Then moving over, there's f of 4. This is not f of 5 because we actually already saw the number 2 over 2. It just was written as 1 over 1. So we're just going to cross it out and then move on and have here, that's, let's see, 1, 2, 3, 4, 5. This is my f of 5. F of 5 is 1/3. F of 5 equals 1/3. And then we'll move this way. That's f of 6. Here's f of 7. There's f of 8. There's f of 9. Here's f of 10. I'm going to cross out the number 4 over 2 because we already saw it as in the form 2 over 1. I'll cross out this next number. Cross out 2 over 4 because we already saw that number. It was just written as 1/2. But this number is new, 1/5. And then we'll move over here and there's a 1/6. And a 2/5 is new. We haven't seen that. Haven't seen 3/4 yet. Haven't seen 4/3 yet. Haven't seen 5/2 yet. I think we haven't anyway. And haven't seen 6 over 1 yet. And so if we keep going in this way and just cross out any number that we've already seen and don't assign that to the next output of f because we want to keep injectivity, then we end up actually seeing every positive rational number once and only once. It's a kind of creative approach to, like, in the first pass only pick up one number, in the second pass pick up at most 2 numbers, in the third pass pick up at most 3 numbers. We actually crossed out one of those numbers though. That's the one that's crossed out in red. But in this way, we actually are describing a bijective function from the set of positive integers to the set of positive rationals. Not by a nice explicit formula like some of the other things we've had, but this does it, and this is kind of usually the way people do this one. It's a little strange. How are we doing? Are there thoughts or questions or wait a minute or something that I can try to address about this? It's a little strange for sure. Just pause for a moment. So if you've not had a chance to yet, maybe this is a kind of time to go back and look at these old questions that were just meant to be fun. These optional problems about one person shows up to a hotel room, and then how do you deal with that? So that, this idea of, like, when one person shows up to a hotel room, it's like you can just, there's all these hotel rooms maybe represented by boxes, and these rooms are all occupied already with people in each of the rooms. But what you can do, so infinite list of people, infinite, but what you can do is you can just say, if you all just scoot over one room, then when one new person shows up, that person can get assigned the first room, which is unoccupied. So there are a lot of these sorts of, or what if, what if a bus shows up that's, with an countably infinite number of people in it, what do you do? And you can take the people in the hotel and spread them out every other room. So if, like, the people in the hotel multiply their room by 2, then all the odd rooms are free, and the first person on the bus can take the first odd room, and the second person on the bus can take the second odd room. And that idea, actually, when you have one bus that's countably infinite, and you have this hotel, like, that's the analogy. It's actually the best analogy to the proof we did last Thursday of when you have 2 disjoint countably infinite sets, what happens to their union. What I'd like to do is take the majority of class, the rest of what we have today to address this proof. So I'd like to talk about the set. We have not brought up a set that's infinite, yet not countable. So let's bring that up. The set of reals is uncountable. Actually, I'm not going to prove this. There's a way to modify the next theorem we're going to prove instead. So I'd like to prove that the set, this proper subset. so this is just the set of numbers between 0 and 1, that this subset of the reals is uncountable. Right? So if just the real numbers between 0 and 1 is uncountable, then including a much bigger set, it seems like that should also be uncountable. So what we're going to do to prove this is that we will prove that this set is uncountable by contradiction. It's not all that often we actually get to practice contradiction. So let's do that. So if we assume for contradiction that the set, we want to prove this is uncountable, so we will assume the negation of that, right? So assume that the set is countable. What it means that this set is countable, it means that all the elements of this set we can just write down in order, right? There should be a first element and a set. I'm not saying that I know what the order is, but what we're gonna do is, because we've got something countable, so we can write the elements of the set. So the first, we can write in a sequential manner. So sequentially, we can write the first element. Let's say R sub 1 is an element in this set of reals between 0 and 1. And then there's an R sub 2, and an R sub 3, and an R sub 4, and so on. So we could write these in order and get all of them. And these are all, just to emphasize here, these are all elements of this set. So how we get, and let's write these each in decimal form. So this is going to look a little messy, but what I'm trying to do is, let me just, so that we can have this all at the top of the next page here, make it a little easier to reference if there's questions later. What I'd like to do then is, here's my first real number, R sub 1. Here's my next real number, R sub 2. Here's my next real number, R sub 3. There's another real number, R sub 4, and so on. And what I'd like to do is, each of these numbers, if they're real numbers between 0 and 1, we can write them as a decimal expansion. The units digit should be a 0. And then for the first number, let's call the first digit d sub 1, 1. And then the next digit d sub 1, 2, and the next digit d sub 1, 3, and d sub 1, 4, and so on like this, right? Some infinite expansion. If you don't have repeating, then eventually maybe d sub 1, 8 is 0 or some, all the rest are 0 or something like that. The second real number, so the first digit that appears after the decimal point, let's give that notation d sub 2, 1, d sub 2, 2, d sub 2, 3, d sub 2, 4, and so on. And then the next real number, so the first subscript, it follows which number in the sequence we have. So d sub 3, 1, d sub 3, 2, d sub 3, 3, d sub 3, 4, and so on. And then 0. D sub 4, 1, d sub 4, 2, d sub 4, 3, d sub 4, 4, and so on. And this list goes on. So I just, can't just keep writing all of these. So these dots that were just drawn here are meant to represent this goes on forever. And just to make sure, I'm going to write it this way. The fact that we can sequentially write all of these down, it means that every real number, so let's use our language for this. Every real number, let me call it S, between 0 and 1, that real number, for all S is in this list. Right? Or said differently, if you like what I mean by in this list, if you want a little more clarity by that, what I'm trying to say is, for all S in real numbers between 0 and 1, S is an element of what you'd have if you built the set, where the set has R1 in it, R2 in it, R3 in it, and so on and so forth. R4, R5. And what I'd like to do is, based on this, I would like to define for you, let us define. So I'm going to right now define R. Now, I don't mean r sub 1, r sub 2, r sub 3. I'm calling this thingy little r. So don't connect little r to r sub 1, r sub 2, r sub 3. So I'm going to define r. And how am I going to define it? R will be a decimal itself. And it's going to be 0 point d sub 1, d sub 2, d sub 3, d sub 4. It'll go on like this. But how I'm going to define what's d sub 1, where d sub I is equal to, and this will be done piecewise, and I just flipped some coins to make some random decisions, but I'll stick to the decisions I made when I first designed these notes. I'm going to use 4 as a digit if d sub I is not equal to 4, and I'm going to use a 7 for d sub I if d sub I is equal to 4. So the point is, these two things that I have there circled in red, they are negations of each other, right? Either d sub I equals 4 or doesn't equal 4. We're actually almost done with the proof. I know this sounds really strange, but like this line that was written right here probably doesn't make a whole lot of sense on its own. So though an example is not ever a substitute for a proof, and an example shouldn't be included inside a proof, I'm including an example in a proof right now so to make some sense of what the hell that what we just said was. So this example, it's not part of the proof, but I want to just include, I'm not including it in the proof, I'm just, as a courtesy, including, let's talk about it to make some sense of this. So for instance, to build an example, so we can write sequentially, meaning there's this existing bijection. I don't know what it is, but I have to just pretend right now that this bijection maps the integer 1, the positive integer 1, to maybe this real number. So I'm just picking an example to make this concrete. So the first real number between 0 and 1, I'm saying is, how about it's 0.2378516, and it goes on like that. The second real number, in other words, what's f of 2, maybe it's 0. Just another real number between 0 and 1. I just picked one. So how about 0.149986062, and on it goes, right? R sub 3, I picked this real number between 0 and 1 just to, like in this sequence, according to this bijective function that's already been fixed. Maybe the third output of the bijective function is this real number between 0 and 1. Maybe it's 0.02709944, and it goes on like that. And maybe the fourth output of the bijective function is maybe this real number between 0 and 1. How about 0.012933126, and something like that. And if we wish I had a little more space. Damn it. Yeah, we'll make do with this. So let's. What I'd like to do is, how am I supposed to define d sub 1? Well, to define d sub 1, look over here, box that in green. And to define d sub 1, so plug in I as 1 right here. Well, take a look. The question is, what's d sub I? We're plugging in 1 for I. So what's d sub 1? Is it 4 or not 4? Is the question. What's d sub 1 anyway? I have to scroll up one more line. Sorry to do this, but d sub 1 is right there. It's the first digit past the decimal point in the first real number. So in this example, it's the number 2. Having a 2, we're in the d sub 1 is not equal to 4 situation. So we're going to sign d sub 1 to be the number 4. So as we write down r, maybe I will do this right over here. So r equals 0 point, and then for d sub 1, we're going to use a 4. That's what our piecewise formula in the green box tells us we should do. Now, what about the next entry here? It's d sub 2. So go back to the green box and you plug in I is 2. So d sub 2 is either a 4 or a 7. And that depends on what d sub 22 is. Well, d sub 22, back up here, it's the second digit after the decimal place in the second real number. And so that second digit in the second real number in my example is a 4 there. Well, when you have a 4, you follow the second piece of this rule, and you're supposed to get d sub 2 is a 7. So put a 7 there. To get the third digit, d sub 3, we again look to the green box, and d sub 3, we need to look at to get d sub 3, we need to know, is d sub 3 either a 4 or a not 4? And d sub 3, if you go back up here, it was the third number after the decimal place in the third real number. So in our example, that's not the 0, not the 2, it's the 7 right there. Well, that 7 is a not 4, right? So I included the 7 because sometimes this is where the confusion comes up. We've just literally follow what the two red pieces say we need to do, and so we're in the not 4 situation, and so we should assign the digit to be a 4. And then for d sub 4, we need to look at what's d sub 4 for. And so let's see, fourth digit in the fourth number is a 9, and that's a not 4, so we should assign a 4. This should be a 4 here. And this goes on. So basically, you need to look at, to get the next digit, to get the fifth digit, you need the fifth number over here. We just didn't write one down because I didn't have time to write all of that for the example. Okay. Believe it or not, so let me pause. How are we doing with what just happened first? How are we doing with how I came up with not this rule, because I just made up a rule, and you'll see why I made up the rule this way in a moment, but how are we with how the rule was applied to come up with this example based on this example? Somebody's got to have a question. Okay, let me say the following. Based on how the number is defined, take a look. It's how R is literally defined. Now, I know I'm using specific examples down here, but it starts with a 0 point. So this already tells you like that how R is defined. Literally, it's 0 point and then digits. So this lets you know that R, just in how this is defined, R is a number between 0 and 1. That doesn't require the example. That's just how it's written, 0 point, just based on the definition of R. The other thing to note is that R differs from, so this number R that we defined, like even in this example, it differs from R sub 1 in the first digit. Take a look. The first digit that's boxed in R1 is a 2. That number is different from the first digit of R, which was a 4. This was by design. These two numbers are different in that digit. We don't even look in any other digit whether they're the same or not. But the R is different from the first number in the first digit, so R is not equal to R1. And then here's the thing. By design, R differs from, I use the thicker pen here, R differs from R2 in the second digit. This was by design. Okay, so take a look. The second digit of R2 is a 4. The second digit of our number is a 7. We designed it, we gamed this. But we don't even need to look at any of the other digits. We just know that our number that we created is not equal to R sub 2 because the decimal expansions of these two numbers differ in the second digit. And R differs from R3 in the third digit. So R is not equal to R sub 3. R differs from the fourth number, which was R sub 4, in the fourth digit. So R is not equal to R sub 4. I mean, all of this was by design, because look at how, now maybe there's a little more appreciation for why the rule was like this. If if the ith digit of the ith number is not a 4, go ahead and use a 4 for our number. If the ith digit of the ith number is a 4, just pick something else, and I just picked a 7 is the point here. But now take a look at what happens is that r is not equal to r sub 1 or r sub 2 or r sub 3 or r sub 4. You know what? R is not equal to r sub, if we keep going, r is not equal to r sub 8. It's not equal to the 8th real number in the list because r and then r sub 8, these two real numbers differ in the 8th digit. So here's what we have. We have r belongs to the interval, but r is not in the set. It's not in this list because r differs from r1 and differs from r2 and differs from r3 and differs from r4. It's not in this list. But that contradicts what we said right up here, that every real number, I'm going to use a new color here, box this in red over here. Every real number between 0 and 1 had to be in the list. But this real number is not in the list. Okay? So this is a contradiction. So what's going on here, just stepping back broadly, is that if you said you had a real list, so say you had if anybody claimed to me that they had a list of real numbers between 0 and 1, and their list had all of the real numbers between 0 and 1, I could, based on their list, construct a number that's not in their list. So it couldn't have happened, is the point. Whew, that is quite a proof. You're not required to recreate this proof ever, but it's one that had to be seen. This is a very important argument that's actually called Cantor's diagonalization argument. I actually want to maybe end class on some informal ideas. So first of all, I'll just say that so Z and Q have the same cardinality, are infinite, but countable. What we have here is this set reals. This is infinite, but this is uncountable. So in some sense, these two sets have the same cardinality, even if one's a proper subset of the other, whereas this set, R, it's like a different level of infinity. I'm speaking informally here right now. Different level of infinity. So I'd like to ask you to maybe, no notes right now. I'm just going to say a couple things for the last 4 minutes of class that are, I think, we're reaching such important ideas from about 110 years ago, maybe a little longer than that, 130 years ago. But the point is the cardinality. So yeah, you're not going to be responsible for what I'm saying next on an exam or a quiz or a homework or anything like that. But I think it's just important to hear these really important ideas, that the cardinality of the set of integers is often written, actually it's usually positive integers. This is often written using the first Hebrew letter, which is Aleph, and then a little subscript 0, and people usually say this not, like in British form for some reason, so Aleph not, or that's not a W, that's actually omega, the final Greek letter, in the lowercase form. Don't get me started on why, because I don't know why these two notations are used for this. The cardinality of the set of reals is usually written using this old German font called Fraktur. So just again, that's and at least in an informal sense, what I hope you're seeing here is that Aleph not is a smaller cardinality than this right here. This is being used because of this word they developed at the time called continuum to describe this situation. So what I want to just mention is that there's this thing called the Continuum Hypothesis. Which I'll abbreviate CH. Okay, CH. This was a conjecture. I'm looking at this old history here. So Cantor, who is actually the one who we claim is responsible for that diagonal argument you saw about creating a new real number out of a fixed list of real numbers. Cantor, this was in the year 1878, conjectured the following. So this is kind of informal, but conjectured that there does not exist a set S, so S had to be a set, such that the cardinality of S was strictly between. So like not equal to, like somewhere between the cardinality of the integers and the cardinality of the reals. Like there could be no set that's in between. There's this conference of mathematicians that still happens every 4 years to award one of the largest possible prizes in math. And in 1900, it was a very pivotal year in mathematics, and Hilbert actually provided this address to the entire audience and came up with these 23 problems as being super important. Some have been solved since, some have not. But amongst these 23 problems, mentions this continuum hypothesis as problem number 1. And you'll actually hear or look in Wikipedia to Hilbert's 23 problems, and they're still mentioned by problem number. And here's the funky thing. In 1940, Gödel proved that this continuum hypothesis cannot be disproved from ZF or ZFC. I can't get into much about ZF or ZFC right now, other than to say we've been playing with sets in a very informal form, and there's something kind of wrong about the way we're doing it, but we're doing what we can with what we have for sets. But the way that we kind of generally operate in our sets is it's called Zermelo-Fraenkel set theory, or Zermelo-Fraenkel axiom of choice set theory, and you cannot disprove. So you can't show that continuum hypothesis is false as of 1940 is something we knew, and then in 1963, Paul Cohen proved that. I'm gonna, in the interest of time, just say this one last line here and then call it. Prove that the continuum hypothesis also can't be proved from ZF or from ZFC. Meaning, if you like the continuum hypothesis as being true, or like the negation of it being true, you can add this to either ZF or ZFC and still have what we believe to be a consistent theory of mathematics. There's a lot of very bizarre ideas going on in this area of math. This is called axiomatic set theory. So we're doing like a very basic level of set theory as we keep kind of doing things. But I did take a class in axiomatic set theory. It was kind of bothersome. I will just say, what I did was, normally in class I show this video for the last 6 minutes, and instead I cut the video suggesting you should maybe optionally watch it. There's a link available. You don't have to watch it, but I thought cut demoing the video here, and instead that's why the first 6 to 10 minutes of class was on a review proof. So we'll call it with that. Oh, a question came up here. Will we ever have to prove that a set is uncountable, like with real? No, you'll not have to do that. It was just sort of like a you just needed to see it once. Like you will not ever be, I promise in this class, you will never be responsible for proving a set is uncountable. Instead of just stating the reals is uncountable, it's like one of these proofs that everybody had to kind of just see once. It's a classic in the area, that's all. Sorry, I didn't see that question until I just looked over. Yeah, stick around if you have other thoughts. I'm kind of done, so it's sort of like, this is one of these class days, though, typically where people want to come up to the podium right after class as I'm trying to raise the board and say, well, what about that? And so, I can stick around for a moment if you've got anything you want to chat about, because it's kind of strange stuff. Why do we use Z positive? Yeah, good question. So it turns out that so one can construct a bijection. So both the cardinality of the integers and the cardinality of the positive integers are equal. Yeah, why not all z? So the point is either of these is what you could. So when you define this Aleph not cardinality, you could assign this to be defined to either of these. Of course, the only way you can do this is if these two sets have the same cardinality, right? So the reason I have made and it is actually a teaching choice I've made to say let's just use the set of positive integers for our like standard kind of set in mind for what's going to be considered a countably infinite set. The reason I did it is because it's a lot easier to make functions from like this kind of thing that we saw last Thursday. It's a lot easier if you have a place to start, right? Like one, two, three. Like otherwise, imagine trying to construct a function um, from integers alone to A union B, and you might say, oh, that's actually going to be easier for A union B because you have like so here's your integers, and you could do this thing of like, okay, the first element of A gets mapped to, you know, one maps to that, and two maps to A sub two, and then for B, I guess, I know B sub one, zero could map to that, negative one, B sub two could map there, and you might say, oh, it would have been easier if we just defined countably infinite a slightly different way, but actually, think about what has to happen anyway when you do like three sets, right? So if your setup is this, like in the homework question, versus this, this somehow this is not really much of a advantage. Like over here, maybe this was, but at some point you kind of have to deal with some interweaving of things anyway, right? And then, but then of course, I think the next question that would come up is, well, then don't you need to prove to me that these two sets, that the cardinality of integers and the cardinality of positive integers, that they are the same? And I normally assign this as a homework question, but I'm not going to because it's a little no, every time I teach this, it's a question I usually ask the students, but I'm gonna just say I think it's a little much, so I'm just gonna maybe point out for you because I think you'd be interested in this. Is that so? How would I define for you, at least in a picture form, a function from positive integers to integers? Well, let me draw my codomain integers here. 0, 1, 2, 3, 4. 0, -1, -2, -3. So what I'm going to do is in red, I'm going to map. So 1 is going to map to, let's try to, 1 will, I'm using the maps to symbol, map to, so then, and then 2 will map here, and then 3 will map there, and then 4 will map to 2, and 5 will map to, so I just start it in the middle. So what's the first integer is going to be the one in the middle, and then I just keep kind of going back and forth, like kind of just spreading around back outside. And there's actually a really nice way to write this in a piecewise format, but at least in picture cartoon form, this you can kind of see it from here. In fact, I could probably just come up with it real quick. Is that f of x should be, let's take a look. So when I have even inputs, if x is even, I should just map to x over 2. And then when I have odds, like a 5, I think I do x minus 1 to get down to 4, divide by 2, and then I just need to make the number negative if x is odd. So cool, that's my rule with this as domain and codomain. Of course, this function needs to be proved to be injective surjective, but I hope the picture shows that it should be. Okay. Sorry I kept rambling, but there's lots of fun things, so that's why. Other questions? Anything that I can... Okay.